Welcome to the online video lecture series of the course Computer Organization and Architecture. In previous lectures, we have completed Unit 1 lectures from 1 to 7, where we have talked about concepts of basic functional units, and we have also talked about their operations. We have talked about registers, what are the symbols used to represent registers, and how register transfer language can be explained. We have also talked about arithmetic circuit, how to design ALU, and we have talked about register transfer, means how instructions related to register transfers can be executed. What are the important steps required to execute particular instruction? In this lecture, we will talk about various problems related to Unit 1. Let us see first problem. We have to write all the necessary steps to execute this instruction. Instruction is given as add R1, R2, R3. So, what is the meaning of this instruction? We have to add the content of register R1 with the content of register R2, and the result will be stored in R3. This operation will be performed in arithmetic logic unit. So, how this instruction will be executed in the processor, and what is the necessary steps required to execute this instruction. So, first, as we know, this instruction is stored in main memory. First, we need to fetch this instruction from the main memory. So, first step is instruction is fetched from the main memory into the processor. So, how this instruction is fetched? First, the address of this instruction which is generated by the PC, and this address is transferred to the MAR register, which is used to hold the address of instruction or data. So, this particular MAR register is connected with the main memory, from where we have to fetch the instruction, and the instruction in terms of some control word is fetched, and it is available with MDR, memory data register, and from MDR it will transfer to the IR, because this data which is fetched from main memory is a type of instruction. So, first it will transfer to the instruction register, and from where this instruction will be decoded in the instruction decoder. So, after decoding, various control signals are issued. So, control signals fetch the content of R1 and fetch the content of R2, because two operands are stored in R1 and R2, and these two values are to be transferred in the ALU, because the addition operation can only be performed in the ALU. So, two operands which are nothing but content of R1 and content of R2. So, these two operands are to be transferred into the ALU, and after transformation the addition or subtraction or whatever arithmetic is operation is given in particular instruction will be performed in the ALU. Here the operation is addition. So, this addition operation will be performed in the ALU, and the output of this, which is in terms of result, will be transferred to the register R3. So, this way we can execute this instruction. So, these are the important steps to perform execution of this instruction, add R1, R2, R3. So, let us talk about next problem, where this transformation operation will be carried out when particular control signal is enabled, and control signal is nothing but it is given in terms of YT2. So, this will be given to the AND gate, and whenever these two values are 1, then this transformation operation will be performed. The content of R1 will be transferred to R2, and the content of R2 will be transferred to R1. So, here in the first problem, we have to draw the block diagram or circuit diagram for this particular instruction, for this transformation control transformation operation. Here you can see the Y and T2 inputs are given to the AND gate, and this is your register R1 and this is your R2 register, and the content of R1, that is n bit data, will be transferred to the R2 register, and this is a feedback connection to R1. Whenever this control is 1, the R2 content will be transferred to the R1, and both the registers are synchronized using common clock, because in your computer system all the components are synchronized through a common clock. So, that is why clock is connected with both the register. So, whenever these two values are 1, the output of this gate will be 1, and this load signal will be enabled. In the same or a common clock cycle, the content of R1 will be transferred to the R2. All the n bits are transferred to the R2, and in parallel to this or within the same clock cycle, all the content of R2 or n bits are transferred to the R1. This way we can understand the circuit diagram. In the second problem, represent the following conditional control statement by two register transfer statements with control function, where the first transformation, that is R2 to R1, will take place whenever p equals to 1, whenever control signal p equals to 1. Otherwise, if the control signal q is 1, then the transformation of data from R3 to R1 will take place. So, how we can write the control function for this particular operation? So, this can be written here, p colon R2 to R1. If p equals to 1, then we can transfer the content of R2 to R1. This can be stated here, and if first part of this instruction is false, so that means the second part is true. So, that is why p dash q is written here. So, if p dash is 1, then p complement will be 0, and q is 1, that means this transformation will take place. The content of R3 will be transferred to R1. So, this way we can write the control function for the transformation of R2 to R1 or R3 to R1. Let us talk about the next problem, which is related with selection of register. The problem states a digital computer has a common bus system for 8 registers of 16 bits each. The bus is constructed with multiplexers. So, in this particular problem, number of registers are 8, and in each register there are 16 bits. In each register there are 16 bits. So, we have to find out how many multiplexers can be connected or can be used to select registers, and what is the size of multiplexer, and how many selection lines in each multiplexers are required. So, you can take the reference of previous problem, as we have done already in previous lectures. So, here you can see all the registers are connected with all the multiplexer. The first multiplexer is connected with first bit of all the registers, and each multiplexer will produce one output. So, how many bits are to be transferred? 16. 16 bits are to be transferred in a parallel manner. So, that is why 16 multiplexers are required. That is why 16 multiplexers are required. Number of multiplexer equal to number of bits of each register, that is 16 in this case. And in each multiplexer, every register is connected in terms of bits. So, that means, if you take the same reference, in each multiplexer we are connecting every register. So, in first multiplexer we are connecting first bit of all the register, in second multiplexer we are connecting the second bit of all the register. This way all the registers are connected with the multiplexer. So, in this case, how many registers are there? There are 8 registers. So, that is why size of multiplexer in this case will be 8 cross 1. 8 cross 1 will be the size of multiplexer, and total 16 multiplexers are required, where each multiplexer will be of having size 8 cross 1. And as we know, the multiplexer can be represented in the form of 2 to the power n cross 1, where n is the selection inputs for each multiplexer to select one input out of given n inputs. So, in this case the size of multiplexer is 8 cross 1. So, this can be written in terms of 2 to the power 3 cross 1. So, how many selection lines are required? 3. 3 selection lines are required in this particular example. Let us talk about next problem. A bus organized CPU has 16 registers with 32 bits in each, an ALU and a destination decoder, and we have to find out how many multiplexers are there in A bus and what is the size of each multiplexer, and how many selection inputs are needed for multiplexer A, multiplexer B, and how many inputs and outputs are there in the ALU for data including input and output carries. Formulate a control word for the system assuming that ALU has 35 operations. So, here in this particular example, you can see we have to transfer 32 bits at a time, and there are 16 registers. These are important inputs. We have to note down the important inputs, 16 registers and 32 bit in each register. So, obviously, how many multiplexers are required in that case? 32, because we have to transfer 32 bits at a time. 32 multiplexers are required in that case. You can take a reference the previous topic which you have we have already discussed when we were talking about control word. We have to write the control word for particular instruction. So, in this example there are 32 bits in each register and there are 16 registers. So, we have to write the control word for selection A, we have to write number of bits for selection A, selection B, selection D and for OPR, operation code, where selection A is the operand 1, selection B is the operand 2 and selection D is used for destination register. This can be selected with the help of decoder, we have already discussed in previous lecture, and this OPR is the operation code. Whatever operation is to be performed by the ALU, that will be given in terms of operation code. So, in this how many operations the ALU will perform? 35 operations. 35 for 35 operations 2 to the power 6 is used. So, 6 number of bits are required to represent operation, because for 32 operations we know 2 to the power 5 it can be represented in terms of 2 to the power 5 bits are required for operation. So, it is greater than 32, that is why we have to take 2 to the power 6. So, 6 number of bits will be given to the operation code. Now, as we said there are 32 bits and 16 registers. To select 16 registers, to select one register out of 16 register, what is the size of multiplexer in that case? The size of multiplexer in that case will be 16 cross 1, will be 16 cross 1. And how many total number of multiplexers? Number of multiplexers are equivalent to number of bits are to be transferred. So, here we have to transfer 32 bits, that is why 32 multiplexers are used, and there are 16 register in our register set, and we have to select one register at a time, that is why the size of multiplexer in that case 16 cross 1. And what is the selection input in that case? So, 16 can be represented as 2 to the power 4 cross 1, 4 bits are required for selection A and selection B. So, 4 bits are given in operand 1 and 4 bits are given in operand 2, because these two are operand bits, selection of operands. So, operands are nothing but they are in terms of register, which registers are to be selected. So, they can be selected with multiplexer A, selection A and selection B input. So, here 4 bits are required for both the cases, and the register set is common. So, destination could be register 1 to register 16. So, that is why decoder size in that case will be 4 cross 16, 4 cross 16. So, because decoder can be represented in terms of n cross 2 to the power n. So, here selection input is 4. So, that is why 2 to the power n is equals to 16. The representation of decoder will be 4 cross 16 in this case, which is written here. And what is the total number of input bits and what is the total number of output bits? Here you can take the reference of the previous diagram of selection of registers in a given CPU control organization, processor organization. You can take the same reference. So, one extra line for input and output is connected in that organization, or in that figure you can see one extra line is required. So, here if particular operation is to be performed in the ALU, so operand 1 is required and operand 2 is to be selected and your destination is to be selected, and operation, whatever operation is to be performed by the ALU. So, bits are required for these operand 1, operand 2, destination and operation code. So, here 4 bits are used for selection, 4 bits are used for selection B and selection A, and 4 bits are used for selection D, and 6 bits are used for operation code. What is the total of this? It is 18 bits. So, total number of input lines in this case will be 32, because 32 multiplexers are here for operation for operand 1 and 32 multiplexers for operand 2 and 1 extra line for input. So, this will be 65 data input lines are required, and same way output will be transferred. So, in that case what is the output line? 32 plus 1, because 32 multiplexers will be used for transferring the result, and 1 output line extra which is given here. So, total number of output lines in this case will be 33. So, this way we can solve the problem for selection of registers. So, come to the next problem. In the next problem, we have to write the control word for particular operation. So, first operation, we have to add the content of R2 with the content of R3 and the result will be transferred to the R1. So, in this case first operand is R2 and the second operand is R3 and your destination register is R1. So, taking the reference of the same example as we have discussed in processor organization, to write the control word, 3 bits are used for operand 1, 3 bits are used for operand 2 and 3 bits to select destination, and 5 bits used to write the operation code. So, here the operation is add. So, in this case this selection A is 3 bit data, selection B is 3 bit data, selection D is 3 bit data and OPR is 5 bit data. So, using the combination of these 3, 3, 3 and 5, we can write the control word for particular operation. So, here the first operand is R2. So, that is why 0, 1, 2 is the selection A value. The second operand is R3. So, 0, 1, 1 is the operand 2, and this result will be transferred to the R1. So, R1 will be the destination register, and for destination register the selection D value will be 0, 0, 1, and for addition operation you can take a reference of that table where various operations operation code are written. For addition we use 00010. So, this will be the control word for first operation. This we have already discussed in previous lecture. In second operation, we have to complement the value of R 4. We have to complement the value of R 4. So, there is no second operand, only first operand is given. So, we can write the selection A is 100 and there is nothing in second operand and this value is transferred to the R 4 itself. So, same values will be given to the destination selection and the operation code for this complementing is 0 1 1 0. So, likewise we can perform all the operation. So, let us talk about last operation. We have to transfer the input value to the R 1. This is simple transformation operation. Since there is no second operand given, so that is why it is blank. First operand is input and we are not having any particular bits for considering input selection. So, that is why we can consider this 000. If we are considering 000 in a particular selection, this will be simply stated as this is the input. It is the direct input taken from the memory. So, control word for this or selection bits will be 000. If it is 000, it states that we are connected with the input and there is no second operand, that is why 3 cross are given here and this value is transferred to the R 7 and for this selection input will be 111 and finally, there is no operation, only transformation operation, all zeros will be given. So, this is the control word table for these operations. Let us talk about next problem, which is very simple problem. We have already done in the previous lecture. We have to convert these infix notations into postfix notations. So, let us talk about any problem, for example, this one. So, in case of reverse Polish notation, we are transferring the operator towards right side of operands. So, in this particular case C problem, if we are going to solve this according to BODMAS, we have to solve this f plus g operation first. So, if we talk about this operation, the solution will be C star D plus E star and if we solve this, so this will come f g plus, because we have to shift the operator towards right during solving. So, now next will be next we will solve E f g. So, this will become C star D plus E f g plus star and in next step we will solve C star D. So, C D star plus E f g plus star and this is your first operand. Now, this is your second operand. This can be solved as in next step which is nothing but A plus B star. If you solve this, so this will become C D star E f g plus star plus. Then you will solve this operation and then you will solve last operation. Finally, you will get in terms of this solution A B C D star E f g plus star plus star plus. Likewise, you can solve this. So, this is the solution of this particular problem and same way you can solve this. The solution of this problem or this infix notation is given in terms of reverse Polish notation A B C D E plus star F G H plus star and divide. So, this way you can convert the reverse Polish notation convert the infix notation into RPN. Let us talk about next problem, which is related to stack organization. If any mathematical expression is given to you in the form of infix notation. So, to solve this mathematical expression using a stack organization, first we need to convert this into a RPN, reverse Polish notation. So, this reverse Polish notation, if you convert this, so this will become 3 4 plus 2 6 plus 1 0, that is 10 star 8 plus star. Here we can change the order of 10 multiplied with 2 plus 6 or 2 plus 6 multiplied by 10, which is same, the order is same. Now, if you solve through stack organization, so first two operands. So, you have the first value which is pushed 3, then you have second value which is again pushed at the top location 4 3, then we have to perform the addition operation. So, in case of any operation, we have to pop top two elements from the stack and do the operation, then result will be stored in the top location of the stack. So, 3 plus 4 is 7, which is pushed back. Then next operand is 2, 2 is pushed at top location, then next operand next value is 6, which is pushed into the top location of the stack. Then next is addition, we perform top two element addition operation and the result is 8, and then next operand is next value is 10, which is pushed back, and then we have to multiply top two element, these two element, the result is 80, which is pushed back to the stack top location. Then next element is 8, we pushed 8, then we have to add, this addition operation is performed and which is pushed back to the top location of the stack. Then the multiplication and multiplication of top two element, which is 616. This way we can find the result of this problem. Let us talk about next problem, which is related to various addressing modes we use in computer organization. So, in this particular case, there is instruction which is stored in the memory and having two words, and initial conditions are given. The program counter is 200, the index register value is 100, and the register R1 is given as 400 and the accumulator. And these are the various locations where some data is stored in the memory. So, first we need to fetch the instruction in various addressing mode. Initially the values are given, and the address part which is given at 500 location and the 500 value, and the address location is 201. So, what are the values in case of various addressing mode if we use? So, let us talk about various addressing modes. So, in case of direct address where we use the direct address value which is given in the second part or second word of the instruction in the memory location 201. So, this will be the effective address where you can get the data. Data is 800. 800 will be transferred to the accumulator. That is why direct address is written as 500, and content of memory location at 500 is 800, which is loaded to the accumulator. Second is immediate operand. Immediate operand mode is simple, whatever the value given at 201 will be transferred to the accumulator. Next is indirect address, where you can get the data of 800 location. So, 800 value is nothing but 300 in the memory location, you can see 800 is 300, which is transferred to the accumulator. Next is relative address mode. In case of relative address mode, the content of PC with the added with the address part. So, here 500, whenever 500 location is executed, the content of PC will be 202. So, 202 plus 500 is 702, and the content at 702 is 325, which is transferred to the accumulator. So, this way we can calculate various addressing modes. So, these are the problems of unit 1. Thank you.